Hey guys, Rao this side. And before discussing anything else, let me share details about myself. My name is Rao, and I worked in this GATE field till now. By GATE 2021 completion, I completed 20 years of teaching experience, 20 years of training GATE students. And I worked in all prominent institute for longer period only, kind of made easier race. And the subjects I take, most of the members know, but electrical machines I'm going to take, network theory I'm going to take, and very soon I'm planning to take power systems also. And this is my code, KNR10. If anyone want to make me more responsible towards your preparation, use my code KNR10. And if you want to motivate me, like, share, subscribe to the channel, our GATE Conqueror. Now coming to here, there are two types of subscriptions, paid subscriptions in Unacademy. One is Plus and another one is Iconic. In Plus subscription, you are going to get live classes, crash courses, weekly tests, doubt solving, rank improvement badges. All those will be there. And if you see Iconic subscription, in Iconic subscription, you are going to get one personal coach extra because Iconic subscription is a superset of this particular Plus subscription. So in Iconic subscription, because a lot of times in our preparation, we need lot of times we will get demotivated. The moment we are demotivated, if in your age limit, at your age, if you can get a ranker, obviously he'll help you in your preparation. And here you are going to get personalized test analysis, preparation materials, okay, all those things you are going to get. Now coming to here, for Plus subscription. For our Plus subscription, if you take the course for 12 months, it is going to be, if you use my code KNR10, it will be 27,225 and EMI facility is also there. And if you take for 18 months by using my code KNR10, you will get for 34,650. And here, 24 months, if you use my code KNR10, you will get the course for 39,600. No cost EMI facility is also there. And if you think of Iconic subscription, the superset, if you use my code KNR10, you will get the course for 40,500 for 12 months. And for 24 months, it is going to cost you 54,000. Okay, with my code KNR10. Now, they thought of increasing the fees from July 1st. But because of lot of demand from students not to increase, they stopped it. But very soon they will increase. So if you want to take the subscription, because GATE is also very nearby, right? So we have to start the preparation very soon. So try to take the subscription soon. And there are two types of batches in Unacademy. One is lecture and another one is Arohan. Lecture batch is meant for GATE or ESE 2022. And lot of prominent faculties are there like Ankit Goyal sir, Aditya Kanwal sir, Suresh V.S. sir, Vishal Soni, B.M. Shankar, B.V. Reddy sir, Tinad Reddy sir. Okay. And Arohan is meant for GATE or ESE 2023. If you are in third year, try to take 23 only, 2 years course only, which is Arohan. And on July 7th, we are starting new batch. And for ECE, for electronics and communications also, lecture batch for 2022 and Arohan batch for 2023. All are very prominent super faculties, including Vishnu sir. With most of them, I worked in many places, wonderful faculties. Now, next thing is, this is about test series. You can have like some free test series will be there in the Unacademy app, and also paid test series will be there for the Plus guys. Now, next thing is, yeah, I have to tell you about this. Every Sunday, normally combat will happen. But here, on coming Sunday, scholarship is very high. And top 3 rankers are going to get free subscription. And remaining members are also going to get some percentage of concession. And people are going to get lot of surprise gifts also. Now, let us start our session. Ours is, what is the purpose of network theory? Why we have to study this subject? And what are the entry points? In the sense, which kind of wings are there in network theory? And exit points, what are the boundaries of network theory? Because without knowing boundaries, if you enter into any subject, we will die like Abhimanyu. Because Abhimanyu didn't know how to come out of Padma Vyuha, right? So point here is purpose. Why we are learning this network theory? Okay. So if you see purpose of network theory, see here, our electrical systems will be there. Right? Means everywhere it can be motor or generator or it can be transistor. Lot of electrical systems are there in front of us. right? So if I have, for example, one electrical system, and with basics only we have to build, and a lot of students will have lots of doubts because of lack of proper basics. Basics are very, very important. Now, if I have one electrical system, for example, this is electrical system. In this electrical system, I would like to know terminal response characteristics. Okay. For example, of course, what is voltage, what is current in next sessions you are going to get from very basic level. And here, but for time being, let me use voltage and current. For example, if this is voltage and the current taken by this electrical system is this much. Now, for which level of voltage, which level of current flow, if I want to know, just like that. Okay, if I want to analyze the practically existing electrical system, okay, this is practically existing electrical system. For example, it's a motor, electrical motor. Now, if it is electrical motor, for given level of voltage, some level of voltage, how much current will my motor take? If you want to know what has to be done, directly take that electrical motor, directly apply that much amount of voltage and measure the current. No, okay, you can connect one voltmeter here and your required level of voltage you can apply and connect one ammeter here. Automatically you will come to know how much current it is going to take. Okay, or else let me tell you, if I think of okay, if I think of BJT, for example, okay, if I think of one BJT, this is practically existing electrical system only. No? Now, if I want to analyze this BJT without knowing network theory and all, what we have to do? Directly, we have to take the transistor, and then means by connecting maybe ammeter here, okay, and by connecting one voltmeter here, and by connecting one ammeter here, okay, we can develop the characteristics. We can develop the characteristic. Maybe for one value of base current, for one value of VCE, how much is going to be the collector current, we will come to know. Directly, we can measure. Means directly after measuring, if you can draw the characteristics, automatically you will come to know about that particular device. No? Okay. Rather than that, while to learn network, these are all called as direct loading tests. Okay. In a practically existing system, electrical system, if you conduct a direct loading test, you need not learn network theory at all. You need not learn network theory. Okay. But for each and everything, can we do direct loading? For example, maybe BJT, if you think of BJT. Okay. If you think of 1 lakh BJTs are there, 1 lakh transistors are there in a chip, for example. If you want to test one BJT, okay, and then that particular BJT analysis can be applied to remaining 1 lakh minus 1 transistors, it's perfectly fine. Okay, for example, if I want to know how much maximum collector current, okay, any boundary conditions, if you want to know maximum collector current my transistor can withstand, if you want to know, what can you do? Means you can keep on increase collector current, and at one point of time, it will be fired. Okay, so transistor is going to be broken. Now, by that time, I will come to know how much will be the maximum collector current taken by the transistor. We will come to know, isn't it not? By direct current. Now, that particular maximum collector current magnitude, we can apply to remaining 1 lakh minus 1 transistors. It's fine. Getting my point, right? So, point here is in direct loading, if I have multiple systems, same kind of multiple systems. For example, if I think of our motor, DC motor or induction motor or whatever it may be, so same type of motors, if I have in multiple numbers, okay, what can be done? We can take one DC motor or some motor and we can conduct direct loading tests and we can apply those test analysis to remaining motors. But for example, in all cases, it may not be possible, right? If you think of big thing, for example, alternator, okay, AC alternator is damn big. The moment alternator is so big, can you dare to do direct loading tests of kind of what maximum speed it can rotate or what maximum current it can handle? Directly we cannot handle because it's crores of rupees. It's very big. So the moment it is very big, we cannot do direct loading test. In an indirect way, if you can find the analysis of that particular alternator, it will be great. Okay, so what we are going to do is, just a minute. Yes, what we are going to do is, rather than direct loading, we prefer indirect loading. That is nothing but network theory. Okay, in network theory, we are going, means if you want to analyze any electrical system for kind of indirect loading analysis, that is called as network theory. Okay, now in indirect loading, what we are going to do is, we are going to take physically existing electrical system. Okay, physically existing electrical system, kind of motor or generator, whatever it may be. So this is physically existing system. Okay, for this physically existing system, rather than directly applying, for example, I would like to know at one voltage level how much would be the current flow through that particular physically existing system. Okay, so for one voltage level, what is voltage current? We'll take care. Okay, ladder. Okay, for current. For one level of voltage, how much would be the current? I would like to know. What we are going to do in network theory is, directly we don't apply. Direct loading test we are not going to do, because in all cases it is not possible. So what we are going to do is, we are going to convert this physically existing system into mathematical model. Okay, so the moment you convert this into mathematical model, okay, that mathematical model may contain resistors, inductors, capacitors, and different types of sources, dependent sources, independent sources. So whatever it may be, this mathematical model, okay, it will be created. Maybe if that mathematical model will contain resistors, will contain inductors, will contain capacitors, or will contain some different levels of sources also. And once physically existing system is converted into mathematical model, what we are going to do? We are going to apply KCL, KVL, mesh, nodal theorems, transits, two ports, or whatever it may be. By applying those many things, for this voltage, how much would be the current? It is not the practical reality. Okay, because practically we are not applying that voltage or that current. Okay, so rather than applying to directly physically existing system, what we are going to do is, means we'll convert into mathematical model. In that particular mathematical model only, we are going to apply different tools. What are those tools? Network theory. Okay, so we are going to apply different tools like mesh nodal, some kind of stuff. And by applying those tools for this level of voltage, how much would be the current? Indirectly, we are going to find without touching the physically existing system. Okay, now you can make a note. Network theory or circuit theory, whatever it may be, it is meant to model mathematically physically existing electrical system. And once the mathematical model is done, upon that mathematical model, we are going to apply different tools. Okay, and by applying different tools, practically existing system, expected results, we are going to calculate from here. Getting my point, right? So here we are going to analyze and we are going to find out the conclusions without touching physically existing system. Okay. Now some people may think that how to convert it, for example, motor or generator. Okay. How to convert this into mathematical model? We are having different tests. Okay. Kind of we see open circuit test, short circuit test, block rotor test. So many tests will be there. By using those tests. Okay. So by using those tests, we are going to convert physically existing system into mathematical model, and upon mathematical model only we are going to work out. And roughly we are going to estimate. It is not physically existing. Okay. Roughly we are going to estimate the current for that particular voltage for this system. So basically network theory is kind of estimation. Okay. It is not like real, because it is meant for indirect loading test. Okay. Anyway, we know the purpose of network theory now. Purpose is over. Now, let us think of entry points. Okay, entry points. Now, if you see entry points, broadly there are like we can classify total network theory into two. That is network theory or circuit theory. Okay. And one more thing is, of course, it is nonsense question, I know, but in some interviews they ask. That's why I'm telling you here. What is the difference between circuit and network? Okay, circuit and network. That is very funny thing to ask, because the reason also I'll tell you at the end. For example, if I have maybe whatever it may be, big network like this, okay, at least one closed path is there, no? See, at least one closed path is there. So means only I'm telling you for the interview purpose only, because it is a wide question. At the end I'll tell you that. Okay, see, the moment you have at least one closed circuit, that can be called as circuit. Okay, and if you don't have any closed circuits, it can be called as network theory. Okay, for example, closed paths are not there. I'll tell you why this is wide also. Like this. Okay, is there any closed path here? No, there is no closed path. So the moment closed paths are not there, we can call this as network. Basically, network is superset of circuit. Okay, because means circuit in the sense at least one closed path should be there, and here network in the sense open path also. But why this question is wide? Okay, not good question. Okay, but of course people are asking, because if you have all open circuits, in a sense, if you don't have even a single closed path also, what is the purpose of having that circuit? Okay, so for example, all open circuits are there, voltages may be there, current will not flow, energy transfer will not happen, power transfer will not happen, nothing will happen. Under that conditions, will there be any physically existing system without having any single closed path also? Okay, because energy transformation will not happen. Okay, so anyway, that is the difference between network and circuit. Now, coming to the point, what are the entry points? Broadly, means I'm going to use from now onwards circuit theory or network analysis or circuit analysis in the similar way. Now, first of all, the circuit theory or network theory can be broadly classified into two subsections. Okay, the first subsection is going to be analysis, and I'll tell you why analysis only questions can be expected. Okay, and another one is going to be synthesis. Okay, analysis means that for a physically existing system, mathematical model will be given. Okay, for a physically existing electrical system, we are electrical engineers, guys. We think everything from electrical line only. Okay, now point here is, for any physically existing electrical system, if mathematical model is given, and that what you are supposed to do, maybe I'll ask, means the particular other may ask you, maybe our Hythe and Kimberly may ask you, at this particular voltage, how much is the current? Or at this particular voltage, or at this particular current, how much is the power absorption, how much is the power delivery, some kind of stuff they can ask. Okay, but mathematical model is given, no circuit is given to you, no. That is analysis. Okay, now in analysis, the advantage of analysis are why that analysis is only there in our GATE syllabus. Or previously synthesis used to be there in ESE syllabus, but now they removed that also. The reasons I'll tell you. In analysis, meaning that our physically existing system mathematical model will be given. In the sense, some circuit will be given. Upon that circuit, you have to apply mesh analysis, nodal analysis, or kind of theorems or whatever it may be. But whatever may be the tool you use, you are going to get unique solution. Unique solution you are going to get. Okay, so if you have unique solution, obviously questions can be asked in ABCD, right? And options they can give. But if you think of synthesis, okay, in synthesis, the problem here is, let me take, of course, about what is a capacitor, what is a resistor, and all. We will see later, not a problem. Okay, but overall look, you know. So in order to understand synthesis, I'm taking this example. That's it. Okay. Now, for example, here some source is there with variable frequency. Okay. So with variable frequency is variable here. Okay. If I keep on increase frequency, for example, if I apply zero frequency, meaning that DC. If I apply DC, capacitor is going to be open circuited. Okay, if capacitor is open circuited, whatever will be the voltage, directly that voltage will come. Now, if you keep on increase frequency, what will happen? Of course, don't focus on capacitor now, because we have to build basics. No, somewhere we have to start. Now, if you keep on increase frequency, reactance of this will keep on reduce. Assume that I have applied infinite frequency, for example. The moment infinite frequency, my capacitance will behave like short circuit. Right? Capacitance will behave like short circuit. So for infinite frequency, because reactance is inversely proportional to frequency, later we will say. So at a very high frequency, it is going to be short circuited. Kind of reactance will be keep on reducing if you keep on increase frequency. At that point, how much will be the voltage? Voltage is going to be reduced. So at low frequencies, input voltage will be output. And if you keep on increase frequencies, output voltage is going to keep on reduce. Right? This is low pass filter. Low pass filter. Okay. Now same low pass filter, can I build in another way? Okay. So same low pass filter, if you want to build in another way, I will erase this. No, it should be there. Okay, I will draw here. Okay. So for example, if I have inductor, resistor, let us analyze this. Again, frequency is variable. Okay. So again, frequency is variable here. Then what will happen? For example, frequency is 0, low frequency. At low frequency, what will happen? Our inductor behave like a short circuit, DC. Okay, so the moment inductor is kind of short circuit, means total input voltage will become output voltage. Right? Now, if you keep on increase frequency, reactance of this will be increased. Okay, for example, kind of infinite frequency, this is very, very high frequency. At very, very high frequency or infinite frequencies, it is going to behave like an open circuit. Okay, so the moment it is open circuit, how much will be the output voltage is going to be 0. Okay, so at low frequencies, it is behaving like a short circuit and input voltage become output voltage. And if you keep on increase frequencies, reactance offered by this will keep on increase. So because of that, output voltage will keep on reduce. For low frequencies, high output. For high frequencies, low output. Meaning that it is also low pass filter only. It is also low pass filter only. Okay, so this is design. Okay, now that design will come under synthesis. Okay, if you want to create any new thing, if you have already physically existing system, we are going to convert that physically existing system to mathematical model by conducting some tests on the physically existing system. And once that mathematical model we got, we are going to apply something in the mathematical model only. We are not going to go back to physical existing system, that is analysis. Now, you don't have physical existing system. You have to design physically existing system. So the moment design, obviously for a designer, many options will be there, right? So means either in this way also low pass filter can be designed, or in this way also low pass filter can be designed. Getting the point, right? Now, that's why for synthesis, the moment it is designed, of course, there are some forms, Foster form, Cowl form. When I attempted ESE, those courses used to be there. Okay, in ESE, that too in descriptive only, because unique solution is not possible. Okay, here for synthesis, multiple solutions will be there. Multiple solutions will be there. So that's why they cannot keep it in ABCD options. Okay, objective. They can keep these questions only for descriptive. But here in analysis, so our main focus is network analysis or circuit analysis, because I told you simultaneously I can use network or circuit. Okay. Now this is going to be the entry point. Our main focus from now onwards is analysis. Okay. Now let us think of exit points, boundaries, which are very, very important. And in boundaries, lot of students will have lot of doubts. Okay. Now, what are the boundaries? Means, what are the boundaries? If you know those boundaries, inside you can plan, you can play. Okay. But without knowing boundaries, we should not enter, because physically the existing system is different. Our model is going to be different. While converting this physically existing system into mathematical model, we have to keep these points in mind. Okay. Now, coming to the boundaries. First of all, network, mathematical model, we are assuming that it is linear. Okay. Of course, linearity everybody know, but don't think that way. Like we have to analyze. Okay. Now, second assumption is lumped, and the third is it should be finite. One important interview question is there here in finite. Okay, means our physically existing system, if it is finite, then only will be converted into, we will be able to convert that particular physically existing system into mathematical model. Okay, LLFP, it should be passive. Okay, this is meant for systems. It is not kind of elements, because you may ask me, sir, passive element, don't add element here. Okay, passive element, where is active element? No, it's not like that. This is passive system. Okay, and after some time we are going to discuss active elements, passive elements. That is different, and this is different. Okay, kind of cell we use, right, in multiple ways. Anyway, PVC, it should be bilateral, and the bilateral also we are going to discuss LLFPVC, causal, and the timing variable. These are the few things. Okay, we are going to assume, then only we are going to enter into network analysis. Now, let us think of what is meant by linearity. Each and every one, let us discuss. Okay, and stay tuned, because there are some one interview question here, one interview question here in timing variant. Okay, now let us think of linear. What is meant by linearity? About superposition and all we'll discuss later. Okay, if excitation to response, what is excitation? Excitation is the input, response is the output. Okay, so means what is the relation between excitation to response? If it is maintaining homogeneity, we call it as linear. Okay, for example, if I think of maybe some excitation here, in the sense input here and output here. Okay, and if it is maintaining straight line, let us think of maybe 45 degrees slope. Then what is going to happen? If I have x here also you are going to get x only. Okay, x only, input will become output because 45 degrees slope. Now, if I double this, it's also is going to be doubled. Meaning that if input is increased by k times, output also should be increased by k times. Is the condition of linearity. But will our practical systems linear? No. Don't think that way. Okay. Now, anyway, means linearity rule, meaning that if input is increased by x times or k times, output also should be increased by k times is the main criteria. Okay. Now, coming to the point. In network theory, in network analysis, our linearity is defined between voltage and current. Okay, and about more in depth of this we'll soon see. Okay, but here one point we have to understand. What is that? See, practical system, practical battery, for example, practical generator. Okay, or practical motor, nothing can be linear completely, because there are again some conditions to meet. Okay, anyway, point here is if I have practical battery. Okay, so this is practical battery, this is system, and for this practical battery, let me connect one voltmeter. Okay, let me connect one voltmeter here. Voltmeter I connect, and I'm trying to observe the voltmeter reading. For example, at starting it has shown 12 volts. Car battery, 12 volts battery. At starting it might have shown 12 volts. Now, what I'm going to do is, let me add resistor here. Okay, of course, about these sources, resistors and all, we didn't discuss, but gradually we discuss, not a problem. Okay, at least basic terminology we know already, right? Now, for example, I connected resistor, and this is variable resistor. It's not constant resistor. And when that resistance is infinite, it has shown 12 volts. And let me reduce the resistance. We want to be increased. V by R. Okay. Now, if you try to draw the characteristics of the practical, what do you say, battery, how the characteristic will be? The characteristic will be between voltage and current. Okay, between voltage and current for a practical any battery, it will be voltage here. If I think of current here, and it will not be straight line like this. It will not be straight line like this. Rather than that, it is going to maintain some nonlinearity. Nonlinearity. But I said that system should be linear, then only a kind of straight line, then only we should be able to model, or we should be able to analyze in network theory, because network theory is a virtuality. How to use network theory after knowing these boundaries, and inside the boundaries only we are supposed to use network analysis properly. Okay. Now this is this orientation. Okay, is showing you like kind of non-linearity here. Okay. Now how to model this? How to model this? Okay. What we are going to do is we are going to have the range, right? Maybe this battery might vary from operating points between here and here. Okay, so operating points are varying from here to here. Maybe it is the least current level, it is the maximum current level for its operation. Okay, so this is the least current level, that is the maximum current level for its operation. Then how to model that battery? Because physically existing system has to be modeled, right? Okay, so what we are going to do is we are going to make a straight line here. We are going to make a definitely error will be there, but we will try to reduce the error, mitigate the error. Okay, now we are going to take a straight line here. During this straight line, okay, so in between least and maximum current operating points, in between these two operating points, we are going to model this with this particular practically existing system. This particular practically existing system is there now. This particular practically existing system we are going to model like battery in series with resistance. This resistance value will be decided by this particular thing. You understand my point, right? For example, if you want to take, let me take blue. Okay, if you want to take from operating point from here to here, operating point from here to here, then what about the slope is going to be reduced much. Okay, so means from this point to this point, if you want to operate battery, okay, physically existing battery, it is not voltage source, it's battery. Okay, battery system. Okay, now if you want to operate from here to here, then it is going to be red slope will be different and this slope will be different, obviously. So this resistance value has to be changed in the model, because multiple times we feel that network is given. Okay, network is given, apply KCL, KVL, and we are going to get the solution, that's fine. But that resistance value may have to be changed while converting a physically existing system into mathematical model. Okay, and one more thing is here. If you take boundaries from here to here, what about the error we are getting? What about this is real one, black one is real one, right? Black one is real one, and blue one is virtual, estimated. Then error also would be more known. Okay, let me tell you one thing. If you are having physically existing system, one system is there, and for some voltage level, maybe let us think of for 10 volts, 2 amperes current is flowing in the original system. Okay, now that particular system is being converted into mathematical model, and upon that mathematical model, mathematics, network theory, upon the mathematical model, you conducted, like you used some kind of tools. It can be KCL, KVL to mesh model to theorems to anything. Okay, you use some tools in this particular model for 10 volts. For 10 volts, basically physically existing system for 10 volts 2 amperes is going, already physically existing system. And in this model, for the same voltage level of 10 volts, if you calculate how much it should come, roughly 2 amperes should come, error should not be more. Getting my point, right? So in physically existing system for 10 volts, if you get 2 amperes between some terminal response characteristic, in a model And after analyzing the model by network analysis also, for 10 volts, almost 2 amperes should come. Then only this particular conclusion can be applied to physically existing system. Right? So our purpose is, without touching physically existing system, we are supposed to estimate the terminal response characteristics of that physically existing system. You understand my point, right? So point here is very simple. Error should be less. Whatever physically existing system is giving, almost in this, almost same thing if you can get, your mathematical modeling is perfect. Okay. Now, point here is linear. Networks analysis is meant for linear only. But physically existing systems are non-linear, outrightly I'm telling you. Okay. For physically existing systems also to be linear, some conditions are there, it's a different story. But almost all, let me use this word, almost all physically existing systems are non-linear. And network analysis is meant for linear. So how you are bridging this gap? You are bridging, this is non-linear, right? Our black, see here, our black is non-linear. See, our black is non-linear. This is original physically existing system characteristics. Okay. And what you are trying to do, by taking some operating region, you are assuming that it has a linear. Meaning that linearizing effects of non-linearity. Okay. So though physically existing system is non-linear, maybe in the operating range we are assuming it as linear, such that it will make our analysis so easy. Okay. And that too, while studying network theory in your BTech or diploma, your age would be much less. You would be kid, right? So being a kid, non-linear and all, people cannot understand. Okay. First, they will our system will introduce you to linearity. That doesn't mean that you need not learn non-linearity in future. No. For electrical engineers, they have to learn non-linearity in machines a bit. Okay. So in machines, we are going to learn non-linearity, but we are not going to analyze much. But in masters, once you enter into MTech, by using some different algorithms or numerical methods, so many tools will be there to analyze non-linearity also. Okay. So conclusion is very simple. Though physically existing system is nonlinear, by using linearizing effects of non-linearity, we are converting it into linear. And we are, we are going to apply network theory for it. Get my point, right? And about the original non-linearity, we are going to learn later. Now, let us think of lumped. Okay, based on this also, one interview question is there. Okay, let us think of lumped. Here, lumped meaning the distribution of the spatial distribution of the system, we are not going to consider into account, that's it. Okay, meaning that maybe if I have one wire here, okay, of 1 meter or whatever it may be, that wire, if you convert it into resistance, if you model the resistance of the physically existing system into mathematical model, means this length is 1 meter. What is this length? Nothing. It's a model. That's it. Okay. This is lumped parameter model. Okay. And when to go to distributed parameter model also, we have to see. Right. Now, point here is, okay. Okay. What is lumped? When should we go to lumped? Because if physically existing system for 10 volts, if it is giving 2 amperes, my mathematical model also, after using our tools of the network theory, for 10 volts, it should give almost 2 amperes. Right? So, in that purpose, lumped parameter model. What is lumped parameter model? Okay. Now, let us see here. If I have one system, some system, or maybe wire only, and this wire length is 1 meter. Let me assume, you will come to know gradually. Okay, because this can be directly connected with the power system. Long line analysis. Means why in long line analysis we have to go to distributed parameter model. Why in short and medium in power systems we need not go to that level. Okay, you will understand now. Now, if I hit here with some electromagnetic wave, it will come out from here after some time delay, Time delay, it should be there because as per theory of relativity, nothing can go beyond light velocity. And fortunately, our electromagnetic wave velocity is also light velocity only. Now, what is velocity of our electromagnetic wave? Actually, don't focus on the time delay, but rather than focus on the information. You'll get to know soon. Just wait. Okay. Now, what is velocity of electromagnetic wave? This is 3 into 10 to the power of 8 meters per second. Okay. Now, let us understand what is wavelength lambda. Okay. Wavelength lambda equal to V by F. This is not voltage power. This is now its velocity of electromagnetic wave. Okay. Now, velocity of electromagnetic wave is fine. Meters per second divided by frequency will be in H or cycles per second. Cycles per second. Okay. What you are going to get? Seconds, meters per cycle. Okay. Try to understand because many things we can make it very easy by trusting dimensions. Okay. So this is going to be 3 into 10 to the power of 8 divided by F. So many meters per cycle. Meaning that my wavelength, if you consider, my wave will travel those many meters after calculation of this, those many meters per cycle. Okay. Now, how many meters per cycle will be decided by frequency, right? Now, let us think of frequency. Yes, let us consider maybe 3 different cases. Okay. Now, let me consider first case as lambda equal to 3 into 10 to the power of 8 divided by 3h. Because normally I take the same numbers because it would be easy to visualize. Okay. Let me consider frequencies 3h. 3 cycles per second is going to be 1 into 10 to the power of 8 meters per cycle. Just stage 1, you will come to know. Okay. Or 10 to the power of 5, 1 lakh kilometers. 1 lakh kilometers per cycle. So, the same electromagnetic wave, if it hit here, and in one cycle of information, you will get gradually sorry. In one cycle, this will travel to 1 lakh kilometers, our electromagnetic wave. Now, let us take the second case. Second case, lambda equal to 3 into 10 to the power of 8 divided by. Let us consider frequency is increased to 300 megahertz. Frequency is increased to 300 megahertz. So, it is going to be 300 into megahertz. Second case. Then how much it would be? 62833 is going to be 1 meter per cycle. Focus here. So, in the first case, if your operating frequency is 3H, then before losing one cycle of information, okay, my wave will travel 1 lakh kilometer. And in the second case, in order to travel my wave from here to here, it will consume one cycle because this is 1 meter per cycle, one cycle will be consumed. Okay. Now, let us think of another system. Lambda equal to 3 into 10 to the power of 8 divided by maybe 300 gigahertz. 300 gigahertz. Okay. Meaning that 10, 3, 3, 1 by 1000 is going to be 1 millimeter per cycle. Now you will get the clarity. See here, for example, if my same electromagnetic wave velocity is constant, 3 into 10 to the power of 8, 3 into 10 to the power of 8, 3 into 10 to the power of 8, but means after starting my electromagnetic wave here, before it reaching here, how many cycles of information we are going to lose? Try to focus there. You will get the idea. Okay. Now, see here. For example, in this case, 1 millimeter per cycle. Meaning that if I hit my, let me use black only, means if I hit my electromagnetic wave here, 1 mm per cycle. After electromagnetic wave, in order to reach 1 millimeter more, it will consume 1 cycle. After 1 millimeter, it will consume 1 cycle. Okay, such that in order to get my electromagnetic wave from here to here of 1 meter, it will take 1000 cycles. Sorry. Okay, it will take 1000 cycles. Try to understand this properly, because basics are very much important. Basics are very much important. We have to understand proper way. At starting, we will learn slowly, not a problem. Okay, but once basics are built, you are going to, it will be very exponentially. Our perception levels will increase very exponentially. Anyway, means for this wave to start from here and to reach here, it will take 1000 cycles. Okay, now if I go ahead with, if I convert this into a simple network theory. In network theory, once electromagnetic wave enters here, means immediately the electromagnetic wave goes here is the primary concern. Okay, that is the assumption there. But here, if you use network theory for this case, if you use network theory for black case, okay, then what is going to happen? You are going to miss 1000 cycles of information. Okay, or see here in network theory. See here in network theory. Okay, forget about it. Let me give you a practical example. Networks, we don't get kind of velocity of electromagnetic wave and all, but in EM theory, traveling waves will be there. In our power systems, long lines, traveling waves will be there. EM theory, traveling wave will be there. But in networks, or short or medium line of power systems, we don't get velocity or traveling wave concepts. We don't get. Why? Because the moment, for example, to start from here and to reach here, maybe I told you now, I'll tell you a practical example. Let us think of one incandescent lamp at your home. Incandescent lamp. Somewhere switch will be there, no? Switch will be there for the incandescent lamp. Now switch on incandescent lamp. Switch on incandescent lamp. Immediately it will glow, right? Immediately it will glow. That is network theory. But let us think of traveling wave concept. If you switch on here, switch is here, lamp is here. Okay, so if you switch on, if you think of our traveling wave, electromagnetic wave has to travel from here to here to here to here, and then only our bulb will glow, meaning that electromagnetic wave or traveling wave, right? So at our home, the moment you switch on, immediately it will glow. Network theory. And if you switch on, it will take some time. That is wave propagation. Now, point to be noted here is, because we have to give approximate mathematical model which should be suitable to get estimated value as more nearer to as practical value of the physically existing system, right? Physically existing system, maybe for 10 volts, 2 amperes. For mathematical model also, for 10 volts, almost 2 amperes you are supposed to get, right? Now, coming to the point. See here, in our network theory, velocity of electromagnetic wave is assumed to be infinite. We are not going to assume it as finite. For example, see here, in this case, at any cost, you have to go with distributed parameter model. Why? Because if you go directly with network analysis approximation, whatever the wave here, instantaneously it should come out here. But if you assume that way, these 1000 cycles of information you are going to lose. Get my point, right? So point to be noted is very simple. See here, in this case, 1000 cycles of information you are going to lose. In order to retain the information of 1000 cycles, compulsorily you have to restrict yourself to the distributed parameter model. Now, coming to here, 3 Hz, our power frequency 50 Hz. Okay, then in order to change 1 meter, in order to travel electromagnetic wave within 1 meter, how much how much time or how much percentage of information you are going to lose? Okay, see here, within kilometers per cycle. So the moment it hit, means within 1 cycle lose, Okay, we are going to lose information, right? So within one cycle, it is going to travel to 1 lakh kilometers. In order to travel to 1 meter, how much percentage of information you are going to lose? Almost nothing. Almost nothing. Okay, so point here is very simple, very simple. In this case, go with network theory. You are not, because 1 lakh kilometer per cycle, and it has to travel only 1 meter. Right? It has to travel only 1 meter, meaning that you are not going to lose much information, so you can go with network theory. Physically existing system, velocity will be there. But we are neglecting that velocity and we are making it as infinite, such that instantaneously it is going to travel, because for physically existing system or mathematical model, almost same results we are going to get. Now, in this case, at any cost, you have to go with distributed parameter only, because 1000 cycles of information you cannot lose. Getting my point, right? Now, you can write one point here. See, lambda, because loss of information, it only will tell if it is very, very high compared to length of the physically existing system. Okay, here physically existing system, length I considered as 1 meter, and lambda I got 1 lakh kilometer. It is very, very high. So whenever lambda is very, very high compared to length in the sense maximum side. Okay, length, width, breadth will be there, we know. But whatever is maximum, I'm considering it as length. Okay, our physical existing system, maximum length we are going to take. If it is very, very less compared to wavelength, then we can assume it with lumped parameter model. And in network, we are going to analyze lumped parameter circuits only. Okay, and if lambda and L are comparable, okay, in our long line power systems, when lambda is comparable with L, then you have to go with distributed parameter model. Okay, make a note of this. Now, let us think of linear lumped finite. Good interview question. Okay, so let us think of what is meant by finite system. What is finite? What if everything is finite only? If you think of battery, okay, this much size will be there. Or if you think of transistor, this much size will be there, maybe in nanometers. Okay, and if you think of alternator, very big, but that is measurable, finite only. And if you think of motor, it is finite only. All electrical systems are finite. Then why to specifically define finite here is the point of interest. Getting the point, right? So, see here, all of our physically existing systems are not finite. That's why they define finite. Okay, this is very popular interview question. People will ask you, networks is meant for finite systems. Why did we define finite? Meaning that we should have got infinite system, no? We should have got infinite system. What is the example of that infinite system? People ask. Okay. Now, if I think of, means after this you will understand finite. Okay. So, I know sphere. I'm very bad at what do you say, spellings. Spelling you can catch it, but I know sphere, you know, right? I know sphere means it will be around our globe, Earth. Now, I know sphere, and in order to transmit our radio signals, AM signals and all, in order to transmit radio signals from one place to another place, we will shoot the signal to ionosphere. Ionosphere will reflect it to another place. Okay. Now, ionosphere, ions, electrical. Is it electrical system or not? Yes, electrical system. But is it finite or infinite? It is infinite. It is infinite for our level. That's why we cannot analyze ionosphere. We cannot analyze ionosphere by using what they say network theory. Now, you know what is meant by finite system, right? Finite system in the sense means the space, what they say, orientation of this particular system should be finite. For except this, remaining all whatever the systems we see, everything is finite only. Okay, motor is a finite, or BJT is a finite, or SCR is a finite, or kind of whatever it may be. All electrical systems of our analysis or of our electrical engineering analysis is going to be finite only. Okay. Now, let us think this. Let us see LLP, passive. This is about passive system, not about passive element. About passive element, we will see later. Okay, this is about passive system. What is meant by passive system? See, wherever conservation of energy is accepted, that is passive. Okay, if you think of our gravitational field, if I think of this as a mass, okay, so if I expend some energy, if I spend some energy, it will go up. If I take that energy back, it will come down. Okay, whatever the energy I supply, it will deliver the same energy or not? Yes. Then that field is called as conservative field. Wherever conservation of energy is accepted in a system, that field is called as conservative field. Okay. Now, similarly, of course, we learned this I think in 9th standard or somewhere. Any system, if you see any system, okay, whatever may be the power supply, conservation of power, conservation of energy, means if power is being delivered by P, some amount of P, power is being delivered, the same amount of power will be absorbed. Okay, so this is in a system, meaning that generator or battery, is it delivering energy? Battery, is it delivering energy? Generator, is it delivering energy? No. Generator is delivering electrical energy but not energy, because generator will absorb mechanical energy and it will deliver electrical energy. So in ideal case, whatever will be the mechanical energy is supplied, same will be given out, electrical energy. If you think of battery, is it delivering electrical energy? Energy? No. It is converting chemical energy into electrical energy. So as a whole, what is the energy being delivered by battery? 0. What the energy being delivered by generator? 0. But of course, as we are electrical engineers, electrical energy is being delivered. That's a different story, by consuming non-electrical form of energy. Okay. Anyway, point here is very simple. And Telegnus theorem we say in future we'll see. Okay. See, conservation of power. If conservation of power is being accepted in any electrical system, obviously it has to be accepted, because in electrical field, we don't have black holes like universe. Okay, if you go to universe, maybe for this to lift energy can be different. This can be different. If I have a black hole here, okay. Anyway, in electrical field or magnetic field, we are not going to have any black hole. So conservation of energy is being accepted. That's why we call electrical field, magnetic field, and gravitational field also as conservative fields. Okay, this is about passive. Now, let us see bilateral. Okay, about bilateral input output, if you see. Okay, for example, system is there here. Let us think of this is excitation, in the sense input, and this is response output. Okay, now if excitation E of t is given, supplied, response is going to be R of t. Now, for example, if I supply same magnitude of excitation this side, here, this side, same amount of response if it get here, that is called as bilateral. Okay, in the sense ratio of response to excitation. Okay, ratio of response to excitation, nothing but transfer function. Ratio of response to excitation is invariant even if you interchange excitation to response. Okay, that is nothing but bilateral. Okay, if I have unilateral systems, means different analysis should be followed. Okay, means for bilateral system, this is our boundary. Okay, because maybe if I think of now, you would get a clarity between traveling wave concept and network theory. Okay, why in network theory reflection, refraction, okay, all those will not happen in network theory, because our basic assumption of network theory is velocity of electromagnetic wave is infinite, and it should be finite system, and it should be bilateral system in that way. Okay, and how to identify these kind of systems, if they give graphs and all characteristics and all, we will see later. Okay, left B is over causal here only we can tell, because about causal, your signals and systems faculty will deal better. Okay. Causal, meaning that after giving excitation only response will come. Response will not come first before excitation. Okay, signal systems guys will tell you acausal, anti-causal, so many things. But anyway, point here is in our network theory, after giving excitation only response will come. Before giving excitation, response will not come. That is causal. Okay. Now let us think. Next thing is time invariant, which is very important. Okay, L L F P B C T I, time invariant. Now you have to understand this properly. Time invariant system. Okay, what is meant by time invariance? Is it possible to have time invariant circuit or time invariant physical existing system here? No. Okay, time invariant system will not be there. For example, if I have kind of resistor, let us think of this length of wire only. Okay, this is the length of wire, and for this length of wire, once I model into a resistance, in the sense this resistance I am going to consider here. For example, this resistance as of now is 10 ohms. You measure that by using some measuring instrument. Okay, now this particular resistance value is 10 ohms. Now, after 5 years or after 10 years, because around it oxygen will be there, so oxidation will happen. Because of oxidation, definitely like outer layer oxides will be formed, and all because of that resistance will be increased. Now, after 10 years, that resistance value became 10.1 ohm. Now, is this time variance or time invariance? As of now, this particular conductor value is 10 ohms. After 10 years, it became 10.1 ohm. Now, this particular resistance value of this particular physically existing system, that is nothing but wire, is it time invariant or not? It is time variant. Time variant. But how can we convert this into like this, and how can we analyze? See, time invariance is not defined for long period, means for infinite amount of time it is not defined. Okay, for 10 years, okay, let me write here. For 10 years, it changed by 0.1 ohm. Okay, for 10 years, change in resistance is 0.1 ohm. If you think of for 5 years, definitely it would not be 10. Okay, it would be increased, but less than 10.1. For 1 year, change will be there or not? Yes. Okay, and for 1 month, change will be there? Yes. For 1 day, change will be there? Yes. For 1 hour, change will be there? Yes. For 1 second, change will be there or not? Yes. And per second, how many cycles we are going to have? Maybe in 50 Hz system, 50 cycles per second, or maybe 500 H, meaning that 500 cycles per second. So per cycle, will it be changed or not? Yes. But that variation, we are not going to consider as a point of interest. Okay, basically time invariance is defined per cycle. See here, 10 ohm, after 10 years it will be changed. 1 day, 1 hour, 1 second, per cycle, how much will be the change? It's going to be very minute. Change will be there, but the change is going to be very minute is our feeling. That's why time invariance. Okay, and time invariance is defined for 1 cycle. Okay, and yeah, these are time invariant, and these are the boundaries. And in this session, we understood 3 things. What is the purpose of network theory? Okay, purpose of network theory is very simple. Like for the indirect loading test of a physically existing system, or to design new physically existing system. To design new physically existing system is called as synthesis, and to analyze physically existing system is analysis, converting into model and all. Okay, and then we understood about entry points. What are the entry points? Entry points are going to be kind of synthesis analysis. 2 wings will be there. Okay, and after that exit points, boundaries. L, L, F, P, B, C, T, I. Okay, so these are the 7 properties: linear, lump, finite, LLFP, passive, bilateral, causal, time invariant. Normally people say LTA systems. It is not like that. Not LTA systems, like LLF, PBC, TI systems. Okay, Thank you guys. Don't forget to like or don't forget to subscribe. Thank you so much.